Okay, so the date is when I sent the presentation to the organizers, but essentially the idea is to present this CR sharp model. And what is this model? Well, many of you know that the CR is an acronym based on the Cox, Ingersoll, and Ross model that was essentially a pricing model for bonds. And then this model was widely applied in finance until when there were issues in terms of, for example, negative interest rates because the idea of this model is that, well, when the interest rates is low, there is a drift that is predominating with respect to the volatility. The volatility goes down, and then the drift is the one that drives the interest rates back on track. And then this model, this CR sharp model, is a solution for this problem, not only for negative interest rates, but also for in instances in which we have clusters of volatility, for example, or we have jumps. So the inspiration is this CR, and then the change that we made was to deal with all the instances, the cases that I mentioned before. So cluster volatility, jumps, negative interest rates, and so on and so forth. So I will present this model, the results of this model based on those currencies for several tenors. So the euro, the US dollar, the Swiss franc, the yen, and the Polish interest rates, as well as an application on other contexts. So not only on interest rates, but also on tourism. And as model benchmark, we used several ones. So like the Allen White, the exponential weighted moving average, the adjusted CR, and so on. But in the literature that I provided at the end, you can find many more, much more than those. So the idea is first to find the right time series. So we replaced the usual Wiener process with the residuals. The residuals of what? Of this optimal ARIMA. And then we first calibrated the ARIMA, and then we take the residuals, and based on those residuals, then we build on this CR process that is the stochastic equation that I will show you later. And why this model is interesting? Well, apart from what I said, is because it's able to model in jumps, stochastic volatility, negative interest rates, and so on. As I said, this model is also effective and by replacing the Monte Carlo simulations, for example. Well, this is the CR model. This is the stochastic process. So this part, this is time. This is the Wiener process. So essentially normal distribution. And this part, the first part is factor that multiplies the drift. So this K is just the speed of adjustment to the drift. So this is the drift. This is the current value of the interest rate, and then this is multiplied for time, the change in variation in time. And so this part is fully deterministic, and this part instead is the stochastic one. So we have the volatility. This volatility is corrected by the square root of the interest rates, and then well, we have the Wiener process, as we said, that essentially is standard normal distribution. So, and then again, the idea of the Cox-Ingersoll-Ross is to say was to say that when this part, when the interest rates are low, and they cannot become negative, because then this prevails. So the long run mean, this is again is close to zero, and this part goes to zero as well. So what matters is just the k times omega. I already mentioned briefly, because we don't have so much time to go into detail, the reason why we want to change this CR model, and then why we don't, why there was an issue when, as I said, the condition of the markets are different from the ones that were assumed by the authors. So there are different solutions, but none of them is satisfactory. So here I mentioned some additional to the ones that I already said. So for example, there is a three-factor model. There is a CR model with time-dependent coefficient, this CR++ by Brigo and Mercurio, and so on and so forth. And this model, the CR sharp model that I propose, has been tested against, as I said, multiple benchmarks. So what is the objective? Well, to follow very closely the structure of market interest rates and to predict in an efficient way interest rates, as well as the volatility of those. So here, there are some technicalities regarding the way in which is built the CR sharp model. But again, as we don't have so much time, let me skip them, because I already mentioned the core. So as I said, first we use a RIMA to calibrate the data, and then we find the residuals, and these residuals should be transformed in a way that are Gaussian. So for example, this is Johnson transformation is one of the ways in which we can do that. These are the equations, but I will skip them. You can find those equations in the reference, as well as in the presentation that I mentioned before, and that I sent to the organizer. And then, well, let's have a look at the baseline models that I already mentioned. The CR adjusted model is just the same model, the same CR model, with some shift, and these shifts were proposed also by others in the literature. And then this is another model that is well known, exponential weighted moving average, and then a white model. This is in which we have additional complication in the structure of the equation. And then let me show you the empirical results. But first, I would like to introduce the directionality of forecasting. What is this? So there are two problems when we make a forecast. The first problem is to be close to the results, to the actual values. And the second thing is quite important for a trader, is to be right in the direction. So if I forecast that the the interest rates will go up or down. Is this forecast correct or not? This is the main question. And then the directionality of forecasting is exactly that. That is the success of predicting the movement up and down with respect to the realization. So, and here you can see the data set. Here we have several currencies and multiple as well tenors. So from the overnight, that is the most difficult one to predict, to 12 months. And then you can see here already some results. So in blue, you can see the prediction as well as the realization. And then the realization for the actual data are exactly like the prediction. So I expect that the change will be, I don't know, 5%, 0.1%. And then, of course, here we have the actual values, and here we have the actual values for the real time series. And then we expect that all the data are aligned, and this is the blue dots. But then we have the prediction of the model, and you can see that those are highlighted in orange, and they're more or less they are aligned with the actual data, so with the realization that are in blue. And especially here, you can see that for the Swiss franc, this is one reason I took this currency, in which the data are completely divided in two parts. And then this CR sharp model is even able to follow the pattern of the time series. So, and here there is an exception, this orange spot. But for the rest, you can see they are very close. The predictions are quite close to the realization. And this is the Blanda-Altman plot, in which you can see the results in terms of confidence level. And then you can see that the out of 113 data points, the outliers are just 9 for the overnight in euro, which I said is the most challenging to predict because there is a little trend there. And similar, we have this, those results for the US dollar. And
yeah, Dr. Orlando.
Yes?
Dr. Orlando, please. Yeah, just we have quickly wind up.
Okay, so you can say the same for the yen and for the Swiss franc, where, for example, for the last one, there are just 2 outliers. And then regarding the different measures, well, you can see that here the percentage of success is 71%, 62%, even 75%, and so on. So I don't have time to go into details here, but then let me skip this. We can find an application of this model to tourism. As you can see, for tourism, we have regular time series, seasonal time series, but because of COVID, you have this spike. And then, well, all models devised for, especially the Blanda-Altman model devised for tourism, fail here. So here we took Hotel Winters, Sarima Garch, and this data machine model, machine learning model, like long short term memory network. And you can see that all fail when there is this spike in data. So when there was the COVID pandemic. And again, the results are similar in the sense that in terms of the directionality plus in terms of error, the CR sharp is able to beat all the presented models. So regarding the conclusion, so what is the benefit? Well, the benefit is that we are good model in terms of error and the directionality, as I said, and then can be used for policy and regulation. Some financial institutions can use this model also for pricing historical zeta spreads. There are investment banks that do that. And then this model is able to extend the forecasting and the predictions and so on, also to other cases, as I mentioned before, tourism, but also, for example, currency crisis. In fact, there is a working paper publicly available on SSRN, in which you can find similar results for the Brazilian currency crisis in the 90s. And so I finished, and then if someone has questions, I'm happy to answer.